Tonight, we are going to sit with the speed of light, not as a number on a physics test, as something stranger. Because the cosmic speed limit is not, in any literal sense, a rule about light. It is a rule about cause and effect, about what happens before and what happens after. Light just happens to travel at that speed because it has no mass to slow it down. That distinction sounds small. It is not. It is the door through which a quiet two-page paper crept in 1994, carrying something extraordinary inside it. Einstein's equations do not actually forbid faster-than-light travel. They forbid the local acceleration of matter past light speed. Locally, that single word has been sitting in the mathematics for a century, mostly unread. And in the past few years, physicists have started reading it very carefully. Before we go further, one honest thing needs to be said. The newest result we are going to discuss tonight is not faster than light. Not yet. But it may be the first physically reasonable step toward the geometry that people always hoped warp drives would need. That distinction between a proof of concept and an actual FTL result is exactly what this video is about. Because the difference between those two things is where the real physics lives. By the end of tonight, you will understand what a warp drive actually is, why it stayed impossible for 30 years, why that may have just changed in a specific and limited way, and what the word real means when a physicist uses it carefully. If this kind of thinking keeps you up at night, in the best way, consider subscribing. It helps this channel reach more curious minds. Now, we begin. Most people, when they hear that nothing can travel faster than light, picture a traffic sign, a cosmic rule posted by some authority, a number chosen arbitrarily and enforced, 299,792 kilometers per second. That is your limit. Do not exceed. That picture is wrong. And the actual picture is stranger and, in a specific way, much more interesting. The speed of light is not a rule about photons. It is a rule about causality, about the logical structure of time itself. Here is the short version of why that matters. If information could travel faster than light, then in certain reference frames, that information would arrive before it was sent. The effect would precede its cause. Your message would be received before you sent it. And if that were possible, you could, in principle, use it to send a signal back to your own past. You could prevent yourself from sending the message, which means the message would not arrive, which means you would send it, which means it arrives. The universe folds into a logical contradiction. This is not philosophy, this is mathematics. And physicists discovered it not by thinking hard about time travel, but by working out the consequences of Einstein's 1905 special relativity paper. The speed limit exists because without it, the word before loses its meaning. Cause and effect become negotiable. The universe becomes incoherent. So the limit is load-bearing. It is not a constraint on engines or rockets or ambition. It is a structural requirement for reality to stay self-consistent. Now, hold that in mind. Because what Alcubierre found in 1994 and what more recent papers have found since is not a way to break the limit. It is something more interesting. It is a geometry in which the limit appears to apply locally, shipped to surrounding space, but does not obviously apply to the space itself. And space, as it turns out, is a very different category of thing than a rocket. Think of it this way. Imagine an ant on a rubber sheet. The ant can only walk so fast relative to the sheet, that is its speed limit. But if someone stretches and folds the sheet, the ant can end up much farther away than its walking speed would normally allow. The ant never broke its own limit. The sheet moved. This is the crack in the wall that Einstein's own equations opened, and nobody noticed it for 90 years. Miguel Alcubierre was a PhD student at the University of Wales in Cardiff in 1994. He was, by his own account, watching Star Trek, specifically the moment the Enterprise jumps to warp speed. And instead of switching off the physicist part of his brain the way most people do when they watch science fiction, he let it run. He asked a specific question. Not, can we build a warp drive? But does Einstein's general relativity forbid the existence of a warp drive geometry? Those are different questions. The first is an engineering question. The second is a mathematical one. And the mathematical one had a definite answer. Alcubierre sat down with the Einstein field equations, which are 10 equations wrapped into one dense mathematical object that describes how matter and energy curve space-time, and he looked for a solution. A configuration of space that would allow a ship to travel from point A to point B faster than light could make the same trip through flat, undisturbed space. What he found was this. General relativity permits regions of space-time to expand and contract. The universe's own expansion is proof of this. Space has been expanding since the Big Bang. Not matter moving through space, space itself growing. And that expansion is not subject to the speed of light. The edges of the observable universe are receding from us at several times the speed of light right now. This is confirmed, measured, uncontroversial. Alcubierre asked, what if you could engineer that effect locally? Create a bubble of space-time around a ship. Contract the space in front of the bubble. Expand the space behind it. The ship inside the bubble would experience no acceleration. No relativistic time dilation, no crushing g-forces. It would simply sit still, locally, while the bubble carried it forward through compressed space. He wrote it up in 2 pages. Published in Classical and Quantum Gravity in May 1994. The title was completely dry. The Warp Drive, Hyper-Fast Travel Within General Relativity. The physics community read it and, for a short moment, was genuinely unsettled. Not because it was wrong, because it was right. The mathematics worked. The geometry was valid. General relativity permitted this object to exist. For about 6 months, the field allowed itself something rare, genuine optimism about faster-than-light travel. Then, someone did the energy math. The energy math was done by several groups almost simultaneously in the mid-1990s, and the answer they got was not merely discouraging, it was cosmically absurd. To sustain Alcubierre's bubble, you would need negative energy. Not a very large amount of ordinary energy, negative energy, energy below zero, the kind of energy that does not appear in our everyday experience of the universe because matter, all matter, has positive energy. A rock has positive energy. A photon has positive energy. And the amount required was not small. Early calculations by physicists, including Michael Fenning and Larry Ford at Tufts University, put the energy requirement at roughly the mass energy equivalent of Jupiter. Not a Jupiter-sized power source. The total mass energy content of a planet 10 times larger than Earth, converted entirely to negative energy. That is what you would need to sustain a bubble large enough to carry a ship roughly 100 meters across. To give you a sense of what that means, humanity's total energy consumption in 2024, every kilowatt-hour of electricity, every liter of fuel, burned every joule from every source on the planet for the entire year, is approximately 600 exajoules. The mass energy of Jupiter is about 1.9 times 10 to the power of 42 joules. You would need to outproduce all of human civilization by a factor of roughly 3,000 billion and do it entirely in negative energy. There was a second problem. The bubble, once moving faster than light, is completely isolated from external signals. You cannot send a message into it from outside. More critically, you cannot send a message out from inside to steer it. The ship inside is sealed in a causally disconnected region. It can be aimed before launch. But once it leaves, no one inside can steer, brake, or abort. The navigator has no controls. Alcubierre himself acknowledged it publicly. His paper was a proof that general relativity permits this geometry. It was not a blueprint for building it. And for the next 20 years, warp drives quietly became the thing physicists mentioned, primarily to explain why they were impossible. Then, in the early 2020s, something shifted, not dramatically, but in the specific, quiet way that physics sometimes shifts, through 2 researchers asking a more precise question. Before the next chapter of this story makes sense, we need to build a real picture of what space-time is. Not the rubber sheet, not the bowling ball on the trampoline. Those are useful starting points, but they leave out the part that matters here. Space is not empty. This is not a poetic statement. It is a measured, confirmed, reproducible, experimental result. Space has a structure. It has properties. It can be curved by mass and energy. It can vibrate in the form of gravitational waves, which were first directly detected by the LIGO Observatory in September 2015. It can expand. It is expanding right now, carrying galaxies away from each other at speeds that, for the most distant ones, exceed the speed of light. That last sentence is important enough to sit with for a moment. The galaxies at the edge of the observable universe are moving away from us at roughly 2 to 3 times the speed of light. Not because they are moving through space at that speed, but because the space between us and them is growing. The distinction is not semantic, it is physical. And it is precisely what makes the Alcubierre geometry possible to write down without violating special relativity. Now think about the Big Bang not as an explosion into pre-existing space, but as an expansion of space itself from an extraordinarily small, dense state. Space was created. Space has grown. In the earliest fractions of a second, during what cosmologists call inflation, space expanded so fast that regions smaller than a proton became regions larger than what is now the observable universe, without violating any physical law, because space itself was expanding, not anything inside it. This is the physical context in which Alcubierre's geometry sits, and it is the same context that two researchers began taking more seriously around 2020. They were not asking whether warp drives were possible in principle, that had been settled by Alcubierre. They were asking whether the specific configurations Alcubierre described were the only ones, whether there were other solutions in the family of warp geometries that did not require negative energy. The answer they found and published in 2021 changed the conversation. The paper was written by two physicists, Alexei Bobrik, then at Lund University in Sweden, and Gianni Martire, working independently. They published it in Classical and Quantum Gravity in March 2021 under the title Introducing Physical Warp Drives. The key move in their paper was a shift in mathematical approach. Previous warp research, including Alcubierre's original work, started with a desired geometry and then asked what energy it would require. Bobrik and Martire reversed the question. They asked, what matter and energy distributions are physically reasonable, meaning positive energy, finite, non-exotic, and what geometries do those distributions produce? The answer was a new class of warp geometry, a family of solutions that do not require negative energy density anywhere in the construction. The matter and energy sources that sustain these bubbles are, according to the paper's analysis, physically realizable in principle, not buildable today, not buildable with current technology, but not requiring anything that contradicts known physics. This was a genuine conceptual shift. Every previous warp proposal was built around the hope that exotic matter would eventually be found or manufactured. Bobrik and Martire's framework starts inside the physics we already know. It asks what warp geometries are available to a civilization limited to positive energy matter, and maps that territory for the first time. The catch, and there is always a catch in warp physics, is that this new class of geometry is subliminal. The bubbles they describe move slower than light. Not fractionally slower, as in almost FTL. Significantly slower, at least in the configurations their initial paper explored. The analysis covered a range of subluminal speeds but did not cross the light barrier. The physics community's reaction was measured, not celebratory. Peer review accepted it. Follow-up analysis began, and the central question that emerged in the years after publication was this: can this subluminal geometry be extended? Can the mathematics be pushed carefully and without breaking the physical reasonableness conditions toward and possibly past the speed of light? In 2024, further work from researchers building on Bobrik and Martire's framework described something they were careful to call a candidate. And that word, as we will see, is doing very specific work. Before we get to the 2024 work, it is worth pausing on what a subluminal warp drive would actually mean. Because there is a tendency, when something does not deliver faster than light travel, to file it under disappointment and move on. That instinct is wrong here. Think about where we currently stand with interstellar propulsion. Our fastest spacecraft, the Voyager probes, are traveling at roughly 17 kilometers per second. At that speed, reaching Proxima Centauri, the nearest star at 4.2 light-years away, would take approximately 75,000 years. The Parker solar probe, at its fastest point during a close solar approach, reaches about 190 kilometers per second. At Parker speeds, Proxima Centauri is still around 6,000 years away. A warp bubble moving at 10% of the speed of light would reach Proxima Centauri in 42 years. At 30% of light speed, 14 years. At 90%, under 5 years. And because the ship inside the bubble is not locally accelerating, the crew does not experience relativistic time dilation in the way they would on a conventional high-speed ship. They age at normal rates. There is also a question about radiation. When a conventional ship moves through interstellar space at a significant fraction of light speed, it encounters a serious problem. Interstellar hydrogen atoms, scattered throughout the galaxy at roughly 1 atom per cubic centimeter, hit the hull with enormous energy at relativistic speeds. Some physicists have theorized that a warp geometry might change how incoming particles interact with the ship, potentially reducing this exposure. But it is important to be honest here. How a warp bubble actually interacts with interstellar matter is not a settled question. It is an active area of theoretical debate. Whether a warp geometry would help, hurt, or simply change the nature of the radiation problem is still genuinely unresolved. The broader point stands. A subluminal warp drive would not be a consolation prize. It would represent a category change in what human civilization could do. Journeys measured in lifetimes rather than geological epochs. That alone would be one of the most significant developments in human history, even without crossing the speed of light. But the 2024 work did not stop at subluminal. And in that paper, researchers used a word that had not appeared in this context before. The 2024 paper, building on the Bobrick and Martyr framework, described what its authors called a subluminal warp drive candidate. One word in that phrase is doing specific technical work, candidate. In physics, a candidate solution is one that has passed the initial mathematical tests. It does not violate the known equations. Its energy-momentum tensor, the mathematical object that describes the distribution of matter and energy in the solution, is physically reasonable. No negative energy required, no infinite energy required. The geometry is self-consistent within general relativity. What the 2024 analysis adds is a more careful treatment of the energy conditions. In general relativity, physicists use a set of tests, the weak energy condition, the null energy condition, the dominant energy condition, to evaluate whether a proposed matter distribution is physical. Alcubierre's original solution failed these tests badly. It required matter that simply cannot exist as we understand physics. The 2024 candidate, according to its analysis, satisfies the weak energy condition. The matter it requires has positive energy density throughout. The geometry itself is more complex than Alcubierre's bubble. Rather than a simple spherical warp region, it uses a layered structure of matter in specific density distributions, but together produce the required space-time distortion. Mathematically, it is closer to an onion than a bubble. The paper is precise about what it is not claiming. It is not claiming this configuration can be built. It is not claiming it achieves faster than light travel. It is claiming that this is a physically reasonable starting point, a configuration that, unlike every previous warp proposal, does not require exotic physics to function. Only physics we do not yet know how to engineer. And then it asks the next question: can this geometry be continuously extended through parameter adjustments that maintain physical reasonableness toward higher speeds? Toward light speed? The answer the paper gives is, possibly, under conditions that are not yet fully understood, which takes us directly to the remaining walls, so we have a physically reasonable warp geometry. No exotic matter, no negative energy, a valid solution in Einstein's equations. That sounds like progress, and it is. But before the optimism runs too far, 3 specific walls are still standing, not philosophical objections, mathematical ones. The 2024 solution is physically reasonable in its energy conditions, but reasonable does not mean small. The energy required to sustain even a modest warp geometry at subluminal speeds is, by current estimates, many orders of magnitude beyond anything human technology can produce or precisely configure. The solution does not require Jupiter mass negative energy. But the positive energy it does require, in the specific geometric arrangement needed, is still vastly beyond current engineering. The exact numbers are still being worked out, but the scaling problem is real and explicitly acknowledged in the papers. The second wall is navigation. The horizon problem that plagued Alcubierre's original solution is partially resolved in the subluminal case. Below light speed, you can, in principle, send signals between the inside and outside of the bubble. But the engineering of how you actually steer a warp bubble, how you adjust its geometry in real time, how you respond to an obstacle or a miscalculation mid-journey, is completely unaddressed. The current solutions describe the bubble moving in a straight line at constant speed. The universe does not cooperate with straight lines at constant speed for journeys measured in light years. The third wall is experimental access. We are operating entirely within the mathematical regime. There is no laboratory test of warp physics, no hardware, no measurement. The space-time distortions involved are far below the threshold of any existing instrument. LIGO detects gravitational waves from colliding stellar mass objects undergoing catastrophic events. The distortions produced by any warp experiment a human civilization could currently attempt would be smaller than LIGO's detection threshold by many orders of magnitude. We cannot yet do physics in this regime, we can only do mathematics. This is not an argument for dismissal. Mathematics that is self-consistent and physically reasonable is how physics has always begun. General relativity was mathematics for years before the 1919 solar eclipse provided experimental confirmation. The mathematical stage is a real and necessary stage, but it is the first stage, not the last. And there is a fourth problem, less often discussed, that cuts closer to the conceptual heart of the issue. It involves what happens to causality if you try to push this geometry past light speed. And it was something Stephen Hawking spent considerable time thinking about. Here is the problem that emerges the moment any warp geometry crosses the light barrier. Faster-than-light travel is mathematically equivalent to time travel. This is not a loose analogy. It is a precise consequence of special relativity. In special relativity, the order of events depends on the reference frame of the observer. Two events that are space-like separated, meaning they are too far apart for light to travel between them in the available time, will appear to different observers in different sequences. Observer A sees event 1 happen before event 2. Observer B, moving at a different velocity, sees event 2 happen before event 1. Both are correct within their reference frames. A faster-than-light signal travels between space-like separated events by definition. From the perspective of a sufficiently fast-moving observer, that signal is traveling backward in time. If you can send a signal faster than light in one direction, you can, in principle, arrange a sequence of such signals, bounced between observers in relative motion, that collectively delivers information to a point in your own past. FTL communication is time travel communication, not metaphorically, mathematically. Hawking proposed in a 1992 paper in Physical Review D that the laws of physics prevent the creation of what he called closed, time-like curves, which is the technical term for paths through space-time that loop back to their own starting point. His argument was not a proof. He called it the chronology protection conjecture. The laws of physics, he suggested, conspire to prevent time machines from forming even when the local mathematics appears to permit them. His specific mechanism was quantum mechanical. When a space-time region approaches the conditions needed to form a closed time-like curve, quantum fields in that region amplify enormously. Virtual particles, which are constantly appearing and annihilating in the quantum vacuum, pile up near the forming boundary. Their energy density diverges. It becomes effectively infinite. And that infinite energy density, Hawking argued, would destroy the very geometry needed to sustain the closed curve before it could complete. If Hawking was right, then any warp drive that achieves true, faster-than-light travel would trigger exactly this quantum back reaction. The bubble would not be a stable structure. The universe's own vacuum would dismantle it at the threshold. The conjecture has not been proven. It has not been disproven. It occupies a specific kind of limbo in physics, widely respected, mathematically supported by partial arguments, and experimentally inaccessible. The geometry needed to test it directly does not exist in any laboratory. We cannot currently create the conditions under which chronology protection would either engage or fail. What it does is set the stakes clearly. A subluminal warp drive may not trigger chronology protection at all. Below light speed, you are not creating closed time-like curves. But the moment you attempt to push that geometry past light speed, you are entering the territory where the universe, if Hawking was right, fights back. There is a category of physics that most people have heard of, and almost no one has correctly understood. Tachyons. Particles that travel faster than light. The popular understanding is that tachyons were invented for science fiction and belong there. The actual physics is more interesting. Tachyons were proposed seriously by physicist Gerald Feinberg in a 1967 paper in Physical Review. He was not speculating loosely. He was working out a specific logical possibility within special relativity. Special relativity describes three categories of entities: those that travel slower than light, with mass; those that travel at light speed, without mass, like photons; and a third category, particles that always travel faster than light and that would require infinite energy to slow down to light speed. These are tachyons. The symmetry is almost elegant. Just as a regular particle requires infinite energy to accelerate to light speed from below, a tachyon would require infinite energy to decelerate to light speed from above. The speed of light is not a wall that tachyons crash into. It is a wall they can never descend to. They exist, if they exist at all, permanently on the other side. Here is what tachyons are not. They are not a loophole for communication. Even if tachyons exist, they cannot be used to send information faster than light, because you cannot control a tachyon precisely enough to encode a message. This is not a practical engineering limitation. It is a consequence of special relativity's own structure. The mathematics that produces tachyons also forbids using them for signaling. The loophole closes before it opens. The deeper problem is that tachyons in most quantum field theories indicate an instability. When a quantum field theory produces tachyonic solutions, it generally means the theory has been built around the wrong vacuum state. The field is sitting at a local maximum of its potential energy, like a ball balanced on the top of a hill. The tachyon is not a particle zooming through space. It is the mathematics telling you the system will roll to a lower energy state. The most famous resolution of a tachyonic instability is the Higgs mechanism. Before the universe cooled to its current state, the Higgs field was in a tachyonic configuration. The instability caused it to settle into its true vacuum state, giving mass to the W and Z bosons and generating the Higgs particle confirmed at CERN in 2012. The tachyon was not a superluminal traveler. It was the universe finding its ground state. So tachyons are real in the sense that the mathematics produces them in certain theories. They are not real in the sense of observable particles you could use to do anything useful. And the dream of a tachyon drive collapses under the same quantum instability argument every time it is seriously examined. In 1948, a Dutch physicist named Hendrik Casimir predicted something that seemed, at first glance, like an impossibility. If you placed two uncharged metal plates very close together in a vacuum, with nothing between them, no air, no light, no matter of any kind, a force would appear, not from the plates, from the vacuum itself. The force was measured experimentally with real precision by Steve Lamoureux at the University of Washington in 1997. The measurement matched Casimir's prediction to within 15%, later refined to within 1% in subsequent experiments. The Casimir effect is real. The vacuum pushes. The reason it does this is quantum mechanics. In quantum field theory, empty space is not empty. It is filled with quantum fields in their lowest energy state. Those fields constantly produce pairs of virtual particles. Particle and antiparticle pairs that appear from nothing, exist for an immeasurably short time and annihilate each other before they can be directly observed. They carry energy. They exert forces. Between the two Casimir plates, The wavelengths of virtual photons that can exist are restricted. Only certain wavelengths fit in the gap. Outside the plates, all wavelengths are available. The result is a difference in radiation pressure. The plates are pushed together by the imbalance in the vacuum. The energy density between the plates is, in a specific and measurable sense, lower than the energy density of the surrounding vacuum. This is what physicists mean when they talk about negative energy density in a laboratory context, not antimatter, not science fiction material. A region where the vacuum has less energy than its surroundings due to geometric restriction. This matters for warp physics because geometries like Alcubierre's require regions of negative energy density to sustain their structure. The Casimir effect demonstrates that negative energy density is not categorically forbidden by nature. It exists. It has been measured. The problem is magnitude. The Casimir effect produces negative energy density at incredibly small scales, and the amounts involved are unimaginably small compared to what any warp geometry would require. Some researchers have proposed Casimir arrays, large arrangements of precisely spaced conducting structures, as a way to aggregate Casimir-scale negative energy. The concept exists in the theoretical literature. It has not been experimentally pursued at any serious scale. But the point is a conceptual one. The vacuum has exploitable structure. And the existence of the Casimir effect means that questions about engineered vacuum energy are physics questions, not fantasy questions. The gap between what has been measured and what warp physics would need is a gap of scale, not a gap of kind. There is a question that appears, with some regularity, whenever faster-than-light physics is discussed. It goes roughly like this. Quantum entanglement allows two particles to be correlated across arbitrary distances instantaneously. Einstein called it spooky action at a distance. If measuring one particle instantly determines the state of its partner, regardless of distance between them, is that not faster-than-light communication? The answer is no. And the reason why illuminates something important about what faster-than-light travel would actually need to accomplish. When two particles are entangled and you measure one of them, the other one does instantaneously adopt a correlated state. This is confirmed by decades of experiment, most definitively by the Bell test experiments that earned the 2022 Nobel Prize in Physics for Alain Aspect, John Clauser, and Anton Zeilinger. The correlation is real. It is instantaneous, and it carries no information. Here is why. When you measure your particle and get spin up, you learn that your partner's particle is spin down, but you had no control over which outcome you got. You cannot choose to get spin up. The quantum measurement is random. Your partner, measuring their particle on the other side of a galaxy, also gets a random result. When they compare notes with you later, traveling at or below light speed, they will find the results are correlated. But neither of you, from your individual measurement alone, can extract any information about what the other measured. You each see random noise until you compare classically. You cannot use entanglement to send a message because you cannot control the signal. It is as if you and a friend each took one glove from a pair before traveling to opposite ends of the world. The moment you open your bag and see the left glove, you instantly know your friend has the right one. But no information traveled. You just resolved an uncertainty that was built into the system at the moment of separation. The entanglement case is therefore fundamentally different from the warp drive case. Warp physics is trying to move matter, or, at minimum, a physical reference frame, from one place to another faster than light. That is a different project from correlating measurement outcomes across space. And that distinction clarifies what the actual challenge is, not to correlate states, which quantum mechanics does freely, but to transport something, which is exactly what warp geometries are working toward. Everything we have discussed tonight, the Alcubierre solution, the Bobrick-Martyr framework, the 2024 candidate, the Casimir effect, the chronology protection conjecture, all of it lives inside a single theoretical framework. General relativity. Einstein's theory of gravity, space, and time. General relativity is the most precisely tested theory in the history of science. Its predictions have been confirmed to extraordinary accuracy. The bending of light around massive objects, confirmed in 1919, the precession of Mercury's orbit explained to the arcsecond, the gravitational redshift of light, measured. The slowing of time in strong gravitational fields, corrected for in every GPS satellite running right now. Gravitational waves, predicted in 1916 and directly detected by LIGO in 2015. The image of a black hole's shadow, captured by the Event Horizon Telescope in 2019. General relativity has not been wrong about a single tested prediction in over a century. But general relativity is known to be incomplete. It is not compatible with quantum mechanics. The two frameworks, each extraordinarily successful in its own domain, give contradictory answers when applied to the same extreme physical situations. At the center of a black hole, at the moment of the Big Bang, at the Planck scale, roughly 10 to the power of -35 meters. At these limits, both theories produce infinities. Neither is trusted. Every serious theoretical physicist expects a successor theory, something that contains general relativity as a limit, the way general relativity contains Newtonian gravity as a limit. And nobody knows what that theory will say about the speed of light. Some approaches to quantum gravity, including certain versions of loop quantum gravity and some models of the very early universe, allow for variations in the effective speed of light under extreme conditions. These ideas are contested, but they're in the peer-reviewed literature. The honest position is this: we do not know if the speed of light is a fundamental constant in all regimes, or whether it is an emergent property of the specific physical conditions of the universe we currently inhabit. We cannot know because we cannot access the regimes where it might differ, and the history of physics suggests a specific kind of humility about that uncertainty. In 1900, Lord Kelvin stood before the British Association for the Advancement of Science and declared that physics was essentially finished. Two small problems remained. One was the photoelectric effect. The other was the ultraviolet catastrophe. Both of those small problems became quantum mechanics. In 1932, Ernest Rutherford, the man who discovered the nucleus, called nuclear energy moonshine. He said that anyone who expected to extract power from the transformation of atoms was talking nonsense. 12 years later, the Manhattan Project produced an atomic bomb. In 1946, Vannevar Bush, who had overseen American science through the entire Second World War, told a Senate committee that a ballistic missile crossing the ocean was beyond the range of possibility. 9 years later, the Soviet Union launched Sputnik. The pattern runs in one direction. The people who declare physical limits are often some of the most accomplished scientists of their generation. They are working with the best information available, and they are systematically wrong about which limits are permanent. This does not mean faster-than-light travel is possible. The pattern of history is not an argument for FTL. It is an argument against certainty about impossibility. Those are different claims. The physicists working on warp geometries today are not claiming that faster-than-light travel is near. They are claiming the mathematical conversation deserves to be taken seriously, that the question is not yet closed, and that there is productive work to be done in this regime even if the destination remains uncertain. Given the track record, that is a defensible position. We come back to the word in the title. Real. In physics, real has a precise meaning that is different from its everyday usage. A mathematical solution is real if it is self-consistent, if it satisfies the governing equations, if it does not violate the known physical laws of the framework in which it is written. The 2024 candidate warp geometry is real in that sense. It exists as a valid object in the mathematics of general relativity. Its energy conditions are physically reasonable. Its geometry is self-consistent. It does not require physics to be wrong. It is not real in the sense of built, not real in the sense of tested, not real in the sense of the blueprint you could hand to an engineering team. The gap between those two meanings of real is approximately as large as the gap between writing down the equations for nuclear fusion in 1939 and building a working reactor. Possibly larger. So is the answer yes or no? Have scientists discovered a real way to travel faster than light? The honest answer is, they have found a real piece of mathematics that does not forbid the geometry warp physics needs. That is not the same thing as a working drive. It is also not nothing. It is where every technology in human history began, not in a factory, not in a prototype, in an equation that someone, working carefully within the rules of the known physical world, found that reality did not contradict. The stars are still where they were. Proxima Centauri is still 4.2 light-years away. The speed of light has not moved. The universe has not renegotiated its terms. But the equations that describe the universe are still being written, and the people writing them have, in the last few years, found something that previous generations did not have: a warp geometry that makes physical sense. That uses real energy. That does not require anything we know to be impossible, only things we do not yet know how to do. There is a difference between those two categories. Impossible and not yet done are not the same thing. And that difference is where physics lives. For a long time, humans looked to the sky and wondered what the lights were. Then they looked more carefully, with better instruments, and found out the lights were other suns. Then they wondered if other suns had other worlds. Then they found those worlds. At each stage, the question that seemed unanswerable turned out to be a question that simply required better tools and more time. We do not know if faster-than-light travel is in that category. It may be the one wall that stays up. Physics does not promise that every question has a convenient answer. That we are, right now, in this specific moment in history, the first civilization on this planet to be asking the question with mathematics precise enough to find physically reasonable solutions. To map the territory between what we cannot yet do and what the universe may not allow. That is not a small thing, and the equations are still open.